Okay, so let's look at this problem. A long solenoid with n equal to 10 turns per centimeter has a cross-sectional area of 5 centimeters square and carries a current of 0.25 amps. A coil with 5 turns encircles the solenoid. When the current through the solenoid is turned off, it decreases to 0 in 0.05 seconds. What is the average EMF induced in the coil? Okay, so let's do a diagram first. So here is the solenoid. Okay, the area of cross section of this solenoid is 5 centimeters square. Okay, surrounding this solenoid is a coil, and the number of turns in this coil are 5 turns. For the solenoid, little n is the little n is 10 turns per centimeter, and we want it in meters, so 10 minus 2 meters, which is 1,000 turns per meter. Okay, all right, so the induced EMF in the outer coil, the red coil, the induced EMF in this coil is equal to the magnitude of the induced EMF is the rate of change of magnetic flux, delta phi, absolute value. Okay, and that's the flux is now the solenoid has a property that the magnetic field is uniform and contained within the solenoid. So the flux threading this second outer loop is just this magnetic field times the area of the solenoid, which is 5 centimeters square. All right, so this is equal to B area delta T, and the magnetic field is decreasing, but we're taking absolute values, so the EMF induced is, the average EMF induced is so delta B by delta T times area, and delta B is B is mu naught Ni. Okay, the final B is 0, so B initial, B final is 0. So delta B is mu naught Ni. Okay, that's how much the flux changes by over 0.05 seconds. Okay, so let's add a sheet of paper. Okay, so the induced EMF is delta B delta T times area equal to mu naught Ni delta T area. Mu naught is 4 pi times 10 minus 7 Tesla meter over amp. N is, we saw that 1,000 per meter, 1,000 turns per meter. I is 0.25 amps, so the current goes from 0.25 amps to 0 in what time? 0.05 seconds, 50 milliseconds. And the area is of the solenoid, area of cross section of the solenoid is 5 centimeters square, and we convert that to meter square, and that's that many meters square. So the induced EMF is, okay, let's take care of powers of 10. Minus 7 plus 3 is minus 4. Minus 4 and minus 4 is minus 8. Okay, so that's 10 minus 8. It's an induced EMF, so it will work out in volts. 4 pi into 0.25 into 5 divided by, oh, I should have taken care of this as well. 10 minus 2. So this actually makes that 10 minus 6, but okay, I'll take care of that. So 10 minus 6 volts, so microvolts. And let's evaluate this number. Oh, goody. The phi cancels. So, and 4 times 0.25 is 1, so it's pi into 10 minus 6. Okay, so the magnitude of the EMF is 3.14 to 10 minus 6 volts. 3.14 microvolts. Okay, that's the induced EMF. That takes care of that problem.